Hey guys, in this video I'm going to solve example 5.20. In the previous video I solved example 5.18 and 5.19, and in this video I'm going to solve example 5.20. So let's just start. Right. So example 5.20 says that show that for a distribution give me a second. Yeah, so we need to show that for a distribution df y naught 1 minus x square upon a square to the power minus p dx, where x lies between minus a and a. This is dx. This is my distribution, and this is my limit for x, right? We need to show that for this distribution we need to show that my rth moment with respect to the mean is r minus 1 a square upon r plus 1 minus 2p mu r minus 2. Also we need to express a and p in terms of sigma and beta 2, right? And we know that the formula for beta 2 is the fourth moment with respect to the mean divided by the square of the second moment with respect to the mean, and mu 2 is also known as the variance, where mu 2 is the variance, right? Let me just right. Yes. So now we don't need to check the PDF here because they haven't asked us anything about y naught, so we don't need to find the value of y naught here. We'll just proceed with finding the mean first. Let's just find the mean first. Mean is my first moment with respect to the origin, or my mu1. I can represent my mean with both of these terms, right? So this will give me x fx dx, and my limits are minus a to a. I need to evaluate this expression, right? So this will become x, and my fx is y naught 1 minus x square upon a square raised to the power minus p dx, minus a to a. Now taking out y naught from this expression because it's a constant term, so minus a to a, x 1 minus x square upon a square to the power minus p dx. Right. Now let's just write this as hx, right? This whole expression x into 1 minus x square upon a square to the power minus p, let's just write this as a function hx, right? So now if I substitute minus x in hx, right? So if I just substitute minus x in place of x here, so h of minus x is equal to minus x into 1 minus x and the square of this upon a square to the power minus p. So this will give me h of x is equal to minus x 1 minus x square upon a square to the power minus p, because this is the square, so this will give me minus x whole square will give me x square, right? So my h of minus x is minus x into 1 minus x square upon a square to the power minus p. So my h of x is so my h of minus x is minus h of x. My h of minus x is minus h of x, right? My h of minus x is minus h of x. This implies that hx is an odd function, right? Hx is an odd function. We also know that the integral of any odd function from the limits minus a to a gives me 0. I have discussed this point in the previous videos, you can check that out, right? So this implies that my mu1, which is my mean, is equal to y0 into minus a to a x 1 minus x square upon e square to the power minus p dx, and this whole term is equal to hx, and we know that minus a to a hx dx is equal to 0. This implies that mu1 is equal to y0 into 0, which gives me 0. So my mean is 0. Just remember this point, my mean is 0. Now we need to show the term rth moment is equal to something mu r minus 2, right? So let's just find the rth moment with respect to the mean. So my rth moment with respect to the mean will be mu r, which is equal to x minus mu1, which is my mean, raised to the power r integral minus a to a fx dx, right? And I know that mu1 is 0, so I can write this as x to the power r fx dx from minus a to a. But we also know that this is equal to mu r dash, right? Why? Mu r dash says that evaluate minus a to a x minus 0 raised to the power fx dx, right? Because mu r dash is the rth moment with respect to the origin. This is with respect to the origin. Right? And this is with respect to the mean. But because my mean is equal to 0, because my mu1 dash, because my mu1 is equal to 0, therefore my mu r is equal to mu r dash, right? So my mu r is equal to mu r dash, which is equal to x to the power r fx dx from minus a to a. So my mu r, now I'll be taking out y0 from this integral because it's a constant term, so I can write y0 minus a to a x to the power r 1 minus x square upon a square raised to the power minus p dx. Now x to the power r can be written as x to the power r minus 2 into x to the power 2, right? I can write this as I can write x to the power r as x to the power r minus 2 into x square. So my mu r will be y0 minus a to a x to the power r minus 2 into x square 1 minus x square upon a square to the power minus p dx. Now I can divide this whole integral by a square and multiply this whole integral by a square. So multiplying and dividing by a square. So this will give me, now if I multiply this term by a square, this will give me a square y0, because a square is a constant term, and I'll be left with x to the power r minus 2 and x square upon a square, right? So I multiplied and divided this integral by a square. Now I can add and subtract 1 here, minus 1 plus 1, and this will give me, and this was my 1 minus x square upon a square to the power minus p dx, right? So this will become a square y0 x to the power r minus 2 r minus 2, and this is 1 minus x square upon a square, right, into 1 minus x square upon a square to the power minus p dx, which is equal to, now I'm just dividing the terms, dividing the integrals. So this will give me, I'm separating the integrals, not dividing them. So this will give me a square y0 minus a to a x to the power r minus 2, 1 minus x square upon a square to the power minus p dx. Multiplying this will give me this, and minus a to a x to the power r minus 2 1 minus x square upon a square. This was power 1 and this is power minus 1, so this will give me minus p plus 1 dx. Right, now we know that this will be equal to mu r minus 2 or mu dash r minus 2, right, because my mean is 0, so both of these terms are same. This is my r minus 2th moment, right? This is my r minus 2th moment because because my mu r minus 2 will be equal to x minus mu to the power r minus 2 fx dx, and wait, my r minus 2 moment will be equal to mu r minus 2 from minus a to a, right? This will be the expression that we need to evaluate, and we know that my mu is 0, this is 0, so basically this is my r minus 2th moment, right? This is my r minus 2th moment, so this gives me my mu r, my rth moment, as a square y naught, my r minus 2th moment. And now we need to evaluate this expression. So I'll be applying ILATE here. Both of these are algebraic terms, so I'll be taking this as my first term, my first function, and this as my second function. So applying ILATE here, this will give me mu, I'm just evaluating the second integral here, I'm just evaluating this part, so I'm not writing this whole expression here or this a square y naught. So this will give me my x to the power r minus 2 1 minus x square by a square to the power minus p plus 1 dx as. Now writing my first function, 1 minus x square upon a square to the power minus p plus 1 and x to the power r minus 2 plus 1, so r minus 1 divided by r minus 1, and this is minus a to a minus now the derivative of the first the derivative of the first function, the derivative of the first function will be minus 2 upon a square, minus 2 upon a square into 1 minus p, right, into 1 minus x square upon a square raised to the power minus p plus 1 minus 1, so minus p, and the integral of the second function which is essentially x to the power r minus 2 plus 1 divided by r minus 2 plus 1, so this will be r minus 2 plus 1, so r minus 1 divided by r minus 1 dx. So I'll be taking this term out, r minus 1, and this minus 2 upon a square 1 minus p, because it's a constant term. Right, so this will give me my this will give me 1 minus x square upon a square to the power minus p plus 1 into x to the power r minus 1 divided by r minus 1, and my limits are minus a to a, right, minus plus, so this will give me plus 2 upon a square into 1 minus p, right, and what I have inside my integral is, and I also have r minus 1 in the denominator, so this will give me x to the power r minus 1 into 1 minus x square upon a square minus p dx, right. So this is my value, minus a to a, right. Now if I substitute my limits in the first term in this expression, so this will become 1 minus a square upon a square. So minus a square, I'll be taking this term out because the square of a and the square of minus a both are equal to a square. So minus a square upon minus a square comes out, and this will give me a square r minus 1 upon r minus 1. Wait, not square here. This will give me a to the power r minus 1 upon r minus 1 and minus a to the power r minus 1 upon r minus 1. Now we know that this is 1 minus 1, so this is 1 minus 1 into this whole expression, right? This whole expression. So this is equal to 0. 1 minus 1 is 0. So this the first term is 0. So what we are left with is my mu r is equal to a square y naught, my r minus 2th moment, and the second term. Now I am left with the second term minus a square y naught into this is my second term, right? So my second term was positive, so this is positive. So this was positive 2 upon a square 1 minus p r minus 1 and the integral of minus a to a x to the power r minus 1 1 minus x square upon a square raised to the power minus p dx, right? So this gives me if I just take this y naught inside, so this will become my PDF. So this becomes a square, right? First I need to remove this a square, because when I when I wrote my r minus 2th moment, my y square my y naught was used inside because I needed that y naught to create my whole PDF, right? My PDF was y naught into 1 minus x square upon a square raised to the power minus p. So my y naught also vanished when I wrote this r minus 2th moment here. So I need to remove all of my y naughts wherever I written this y naught term with my r minus 2th moment. So I need to remove this. So this is just a square mu r minus 2, right? This is just a square r minus 2 mu r minus 2. My y naught was a part of the PDF, so I need to write this. Yeah. So I'm left with this. Now if I take y naught inside, this will also become my PDF. So y naught 1 minus x square upon a square raised to the power minus p is my fx, and this is x to the power r minus 1. My mu is 0, so this becomes x minus mu raised to the power r minus 1 fx dx. This whole expression, and taking y naught inside, this gives me x minus mu to the power r minus 1 into 1 minus x square upon a square raised to the power minus p, and y naught comes inside dx from minus a to a, and I know that my mu is 0, so this gives me x to the power r minus 1 1 minus x square upon a square 1 minus x square upon a square. This gives me x to the power r minus 1 into 1 minus x square upon a square raised to the power minus p y naught dx from minus a to a. This is my mu r minus 1 moment because my mean is 0, like the same that we did in finding the r minus 2th moment. So this is my r minus 1th moment, right? So I'll be just drawing a line. This is minus a to a, and this is a, right? Or let me just write, this is my mu, this whole expression is my mu. This is my r minus 1th moment with respect to the mean, because my mean is 0 or my mean is origin. So I am left with r minus 2 minus, now a square and a square goes away, and y naught also gets vanished when I use it inside the integral. So I am left with minus 2 into 1 minus p divided by r minus 1 into mu r minus 1, right? So I'm just drawing a line here. This is my minus a, right? So wait, this is r minus 1, right? Wait, this is not r minus 1. Wait, I had another r here, right? I had another r. When I find the derivative, I'll be left with another x here, right? 2x. So there's another x here. Wait, I forgot to write this x. So there will be another x here. There is another x here. So this x, when I was finding the derivative, wait, let me just find the derivative and show you guys. So my derivative, I should have another x here, right? If I find the let me just draw a small box here and find. So the d by dx of 1 minus x square upon a square raised to the power minus p, this is equal to minus p plus 1. So the derivative of this term is minus p plus 1 into, I need to draw a bigger box, otherwise this will become untidy. So let me just show you how I wrote another x here. Right, let me just write another x here. So this becomes x to the power r minus 1. This becomes, wait, let me just draw a small box here, right? So the d by dx of this term, of my first term, yeah, so this is minus p plus 1. So this becomes minus p plus 1, and this whole integral as it is raised to the power minus p plus 1, so minus p into, now the derivative of this becomes minus 2x upon a square, right? So I took the term minus 2 upon a square outside, so I'll be left with another x here, right, inside, and I also had x to the power r minus 1 already inside, because this is the integral of the second term. So what I'll be having here is x to the power r, not r minus 1. So I'm just writing x to the power r now directly here, and this will become the rth moment now, not the r minus 1th moment, right? So this is x to the power r, this is x to the power r, x to the power r, right? X into x bar r. So right, so this becomes my now x to the power r into into the PDF. X to the power r into the PDF gives me the rth moment, not the r minus 1th moment, right? I'm so sorry, this is the rth moment, right? So I'll be just writing the last step here now, that my rth moment with respect to the mean is a square mu r minus 2th moment minus 2 into 1 minus p divided by r minus 1 into my rth moment, right? So I can take this term to the LHS. So this will give me mu r, taking mu r common, this will give me just taking, this will give me r minus 1 plus 2 minus 2p divided by r minus 1 is equal to a square mu r minus 2, right? So this will give me mu r, this is r minus 1 plus 2, r plus 1 minus 2, so this will give me minus 2p. So this will give me a square mu r minus 2 into r minus 1 divided by r plus 1 minus 2p, and this is what we need to show. Let's just check if we need to show this only. R minus 1 a square mu r minus 2 divided by r plus 1 minus 2p, right? So we need to show this only, and we have proved this. Now we need to show, we need to express a and p in terms of the standard deviation and beta 2. Now I know that my mu2 or my variance, the square of the standard deviation, this is equal to first let me write the rth moment. So my rth moment is equal to a square r minus 1 mu r minus 2 divided by r plus 1 minus 2p. So my mu 2 will become a square 2 minus 1 mu 2 minus 2 divided by 2 plus 1. I am just writing 2 in place of r. So this will become minus 2p. So this will give me a square mu 0 divided by 3 minus 2p, right? And we know that my mu 0, which is equal to x minus mu raised to the power fx dx from minus a to a. R mean is 0, and also anything raised to the power 0 is 1. So this will give me fx dx raised to the power minus a and a, which is equal to 1, because this is the essentially the area under the curve from my limits minus a to a, right? This is equal to this, the total probability under the curve from minus a to a, which is equal to 1. The total probability or the sum of the whole area under the curve is 1. So my mu 2 or my sigma square is equal to a square into 1 mu 0 upon 3 minus 2p. So my a square is equal to sigma square 3 minus 2p. Now you can find the root also, but this is what we can write as our final step, and they have also left this the term a square as this only, this term they have left, they haven't simplified this further. Yeah, let me just check. So a square into 3 minus 2p into sigma square, right? Yes. So let's just find the value of p in terms of beta 2. So the value of beta 2 is mu 4 divided by mu 2 square, right? Let me just check if the formula that I am using is correct. Yeah. So my mu 4 will be just replacing 4 in place of r. So my formula for the rth moment was a square r minus 1, a square, now 4 minus 1, replacing 4 in place of r, 4 minus 1 mu 4 minus 2, so this gives me mu 2 divided by 4 plus 1 5 minus 2p, right? So my mu 4 is 3a square mu 2 divided by 5 minus 2p. Right, so my mu 4 is 3a square, and my mu 2 was my mu 2 was a square upon 3 minus 2p, right? Or let me just find the value of beta 2 first, right? So my value of my beta 2 is my value of my mu 4 is 3a square mu 2 divided by 5 minus 2p, and the value of my beta 2 is mu 4 upon mu 2 whole square. So let me just write this, 3a square mu 2 divided by 5 minus 2p and mu 2 square. So this and this gets cancelled, so this I am left with 3a square upon 5 minus 2p, right? So my beta 2 is equal to 5 minus 2p is equal to 3a square. So my 5 minus 2p is equal to 3a square upon beta 2, which implies that 5 by 2 minus 3a square by 2 beta 2 is equal to p. So my p is 5 by 2 minus 3a square by 2 beta 2. Now my value of a square was my value of a square was or wait my value of my value of a square was wait. So I had another mu2 here. I have another one mu2 in the denominator also, right? I have another mu2 in the denominator. So this is mu2 beta 2. So this is mu2 beta 2, right? This is mu2 beta 2. I had another mu2 here in the denominator. So this becomes beta 2. Let me just erase some of the steps. I'm so sorry. Let me just rectify my mistake. So this is so this is this gives me 2 into 5 minus 2p 3a square So I'm left with beta 2 is equal to 3a square upon 5 minus 2p into mu 2, right? And now can I substitute the value of a square? So the value of a square was mu 2 into because see my sigma square and my mu 2 is same, so I can write this a square as a square is equal to mu 2 3 minus 2p. So let me just write this as mu 2 into 3 minus 2p. This is 3 minus 2p divided by 5 minus 2p into mu 2. So mu 2 and mu 2 gets cancelled. So I'm left with beta 2 5 minus 2p is equal to 3 into 3 minus 2p. So this gives me 5 beta 2 minus 2p beta 2 is equal to 9 minus 6p. So I can take the p and p terms on one place. So this gives me 5 beta 2 minus 9 and taking 2p common. So I'm left with beta 2 minus 3, right? So ultimately the value of p is 5 beta 2 minus 9 upon 2 beta 2 minus 3, and this is what we needed to show. P is equal to 5 beta 2 minus 9 divided by 2 beta 2 minus 3. 5 beta 2 minus 9 divided by 2 beta 2 minus 3, right? So we found the value of p, we found the value of a square. They have also left it at a square only. They didn't find the root, they didn't find the value of a. So a square is equal to sigma square into 3 minus 2p, and we also showed that my rth moment is equal to a square and mu r minus 2, the r minus 2th moment with respect to the mean, and r minus 1 divided by r plus 1 minus 2p. So we proved all of the parts in this question. I hope you guys like the video. If you have any doubts, just let me know in the comments, and also if I made any errors, just type them out so I can rectify them and improve myself. Now also if you have any suggestions on the different topics that I can take over in the next classes, what I thought was I'll be starting with the cumulative distribution functions of one variable only, and then eventually move on to joint probability distributions. But if you want me to take some other topic, the questions on some other topic, just let me know and I'll upload the videos on those topics. I hope you guys like the video. If you like the video, please subscribe the channel, share the video, and I'll see you in the next video. So thank you so much, and bye bye.